And I collector is alpha I emitter from principles. We got it. And I base is I collector over beta. We have the formula. Also, we got it. Just do them. It's just merit of substituting and do the math. Otherwise, these formula you need to remember them. They are there, and we will use them in many examples. Now, have a look at the difference between when alpha, even if it is small change, as example 0.9 to become 0.99, 0.999. How this reflect on beta? Okay, have a look. I will substitute when alpha is 0.9, I got beta 9. When alpha is 0.99, it was beta is 99. When it is 0.999, it become around 1000. So see, small change in alpha reflect large on beta. Okay, let's take another example on these principles. A certain transistor operated with forward bias of the base emitter junction and reverse bias of the base collector junction has IC equal IE equal, he gave me IC and IE. Find the value of IB. So it's easy because IB is IE minus IC. We got it. Find alpha, also easy because we have IC, we have IE. Just substitute. And find beta. Either I use alpha to find beta, or I say beta is IC over IB. I got it. Now let's come to the characteristics. Okay, common emitter. Just a minute. Common emitter, this means that there's common collector, common base, yeah, but we don't need to repeat all of them. One of them is enough. So common emitter, when the emitter here connected to the ground, it's called common emitter. And we need supply for the collector and supply for the base circuit. This is the base circuit and this is the collector circuit. And we have the formula which say V base collector called V base emitter minus V collector emitter. And the condition for the transistor to be in forward bias. It means V base emitter is forward, V base collector is reverse. Now for the characteristics, you remember for the diode it was in this way. This is ID and this is VDE. This is the forward, this is reverse, it's one graph. But for transistor we have two graphs. One is the input characteristics, which is the relationship between V base emitter and I base. It's look like similar to the forward bias of the diode here. You see? Similar. Quadrant 1. Okay? And the second characteristics is the output characteristics, which is the relationship between V collector emitter and I collector. It look like many curves. Oh, this one, this one, this one, this one, and so on. Why? Because it's based on. So what happened is, if you can see now, based on I base, you are going to get I base from the open input characteristics, and you come, if it is 10, then this is 10 micro, then this is the line you need to deal with. If it is 40, then this is the line you need, and so on. So you start from open circuit characteristics and you move to the short circuit characteristics. With example, it will be more clear. Now have a look here. Okay, load line analysis. You remember we discussed load line analysis in diode. In diode, load line analysis, we use it to find the operating point, or we mean the current and voltage of the diode. The same thing here happen in the let me say the transistor, but the difference is we have two characteristics, input and output characteristics. For this circuit, okay, you can see here, if I go to the input circuit here, okay, we have VBB plus Vn, okay, the voltages DC and AC equal RBIB, which is the drop here plus the drop here, plus V base emitter. Now one time we will assume that IB here is 0 when talking about this line. Okay, then V base emitter will equal to V input plus VBB. We have point. Sometime we will assume this VBE is 0 when talking about this line, the vertical line. Then IB will be the voltage here divided by the resistance. As you can see here, we have another point. Now we make a line. Okay, this is the line. between these 2 points and we intersect here. This point of intersection will give me IBQ. So from the input characteristics, I will find I base quiescent point, operating point. I will take it. I will go to the output characteristics. Now output characteristics is happen in this circuit. It means the collector circuit. This voltage equal drop here plus drop here, as you can see. Again, I will assume current 0, then VCE equal VCC, I have point. Or VCE 0, then IC equal VCC over RC, I have another point. Then I make a line. Now from previous circuit input characteristics, let's assume I got the current IBQ equal 30 micro. Then this is the line I'm looking for, and this is the point of intersection. Now if I go down, I will find VCEQ, the operating point, and here ICQ, the operating point of the current operating point. You see? Now this is how we work using load line analysis to find the operating point, output current and output voltage, ICQ and VCEQ. You remember here, this is the voltage, the maximum value. So when sign here become 1, this is the maximum value. When sign become -1, so it means minus 0.8 Vn, this is the minimum value. Or when sign lead to, you need to write VCC equal ICRC plus VCE. Okay, you will assume VCE equals 0, then find IC. You will assume IC equals 0, you will find VCE. So I got 2 points here and here, and I make a line. Now I will take now the currents. The first current IB was 50 micro, so this is the line. They intersect here. This is VCE I'm looking for. For I base 25, this is the line. They intersect here. This is VCE I'm looking for, and so on. You got it? I bring what I got from input characteristics, I move it to the output. As you can see here, I assume that Vn is 0. I repeat the same calculation, but Vn is 0.4. I repeat the same calculation for VBN is -0.4. So it's repeating the same calculation, but just changing Vn. Now this is what I got. I base IBQ 25, minimum 15, maximum 35. I go to the output characteristics. This is my equation. VCC equal ICRC plus VCE. RC is given 2 kilo. Then when I assume VCE 0, I find IC, or I assume IC 0, find VC. So I got these 2 points, I make a line. Now I come for 25 micro. Where is 25? 15, 20, 25. This is 25. So the point of intersection here. So I make a line. This is VCE at this current, and so on for the others. It's worth mentioning that if I compare the input and output signal, the small hello with large hello, I will find that, you see here, this is in millivolt, this is in volt. This is Vn, okay, V base emitter, and this is Vn, sorry, the input hello, small value, and this is VCE, the large value. First of all, here, let me say 400 milli, it means 0.4. Yeah, but here, see the output, it get amplified, it becomes 7. And also have a look here, the signal here in this direction, the output is inverse. Oh, so this means that yes, I'm doing amplification, but inverting the value of the signal. It's okay since I'm doing the amplification. Also, I would like to mention that our output characteristics contain 3 parts. This first part, when the current is 0 or small, we call it cutoff region. And this part, when current is large but voltage is small, we call it saturation region. Cutoff region, saturation region. And here is the active region. In active region, the transistor work as amplifier. It's amplifying. It's like variable resistance in amplifying the signal. But in cutoff and saturation region, it works as a switch on and off. This to be used for many applications and to be discussed in level 3 in power electronics. But in this semester, we will work only or focus only on the active region, how we amplify signals. Where is the question here? Yeah. V base BB was 1.6. I will change it to be 1.2. What will happen? Okay. I repeat the same discussion here. Vn is 0. Vn is 0.8. Vn is minus 0.8. I got the lines, I got the currents. See now the currents. The current now 15 micro to 35, but the minimum is 1. So it means the range increase. When VBB reduce, the range increase. And this reflected also on the output voltages. It's changed now. Okay. Now just a quick mention for, you may ask, okay, now till now we are discussing NPN diode, a transistor. What about PNP? PNP, the same procedure, but the only difference is the directions of current, as you can see here, is the opposite direction. Voltages is the opposite direction. So when we write the formula here as example for this situation, VBB, this voltage, Kirchhoff in this direction, okay, in this direction, in this direction, minus Vn because it's in the opposite direction, minus the drop across this resistance, plus the voltage here because it is in the right direction. So this is the formula. What about the calculation? We repeat the same discussion. We assume input voltage to be 0, highest value, lowest value. For each one of them, as example, when it is 0, Vn, we assume IB 0 to find V base emitter. We assume V base emitter 0 to find I base. So the same procedure and discussion to be repeated here. Also, we have 3 lines. We got from these lines I base for maximum, minimum, and quiescent point. For collector, this part, for collector, you see the voltage is in the reverse direction, the current in the reverse direction. Also, if we looking from this side, 9 volt minus drop across this resistance plus V collector emitter, the voltage here, okay? And then we use the information given for R and the voltage to find the 2 points. When IC is 0, we find V collector emitter. When V collector emitter 0, we find I collector, okay? Then we have these 2 points, point here and point here. We use the current for base. We got it from the input characteristics to intersect. As example, these are the points. Then in front of them, we have here the output voltage. In this way, we amplify the signal. Microphone, small halo, as you can see, it's go through here, it become large halo. Let me stop here.